David Can here with another question from topic 6.1. We're going to be looking at banked circular motion in this question. And it's important to note that banking will only be considered qualitatively in your test, so you don't need to perform any calculations with banking, just describe it. So for example, for an example of banking, we can look at some sports like racing sports such as roller derby, where competitors go around a circular track and the track is banked. There's an angle to it. And this bank in the track allows the competitors to move faster. And our job is to explain why you can move faster on a banked track than you can on a flat track. So to understand the difference, probably the first step is to understand what happens on a flat track when you move around a circle. So here's a flat track. Here are the roller skates on that flat track. And we'll look at the forces involved in moving in a circle. So here's the roller skate. We're going to move in a circle like this. The first force is maybe the weight. And preventing you from falling through the floor is the normal force. And in this case, in a flat track, the normal force must be equal and opposite to the weight. The floor is preventing you from falling through. So how do you wind up going in a circle? Well, you're pushing against the floor. And you don't slide, you roll, because of static friction. So when you push against the floor to push yourself in the circle, it's friction that's keeping your wheels from sliding sideways. Now friction, we learned in topic 2, can be calculated with the coefficient of friction times the normal force. Which means that there's a limit to how hard you can push yourself in this circle. If you push too hard, if you push harder than the force of static friction, then you're going to slide. Your wheels are going to slide out to the side from you and you're going to fall down. But you need a big force to the side in order to travel fast. Because remember, the centripetal force is mv squared on r. So if you want to go faster, you need a bigger centripetal force. And that centripetal force is being supplied by the force of static friction, which is limited by the stickiness between your wheels and the floor and the normal force. And you can't really do much about either one. So one thing you can do to allow yourself to go faster is to put glue on your wheels. One thing you can do to go faster is to bank the track. So here's a cross-section of the track. We're still going to be traveling in a circle this way. And now our wheels sit on the track here. We'll look at the same forces. There's weight. Weight is down. It's the same weight as before, unless we gained or lost mass. What about the normal force? The normal force is always perpendicular to the surface. So the normal force has to be in this direction. And how long should it be? Well, it needs to oppose the weight. Because again, we're not moving up or down. So the vertical component of the normal force has to be just as long as the weight. Which means that the normal force, which should be a straight line, has to wind up being just a little bit longer than the weight overall, so that it can be just as tall. This means that there is a horizontal component to the normal force, which is helping us move in a circle. So the normal force is contributing to our centripetal force. In addition to that, we could still push against the side of the track with a force of static friction. And the horizontal component of that can also contribute to our centripetal force. So basically, our centripetal force can be much, much greater on a banked track than it can be on a flat track. And if the centripetal force can be greater, then we can move at a higher speed for a circle of a given radius.